All right, finally we are ready to look at factor rings. Let's look at Theorem 14.2, existence of factor rings. So we have a ring R and we have a subring A. Then the set of cosets R mod A, defined as R plus A for R and R, is a ring under the operations of addition and multiplication, the way that we want it to be defined, if and only if A is an ideal. And so, at this point, this shouldn't be too big of a surprise to us because we came up with the idea of an ideal so that we would be able to define these two operations, addition and multiplication, in the way that we wanted them to work. So let's look at example 4, where we are seeing two factor rings in action. So in part A, we are looking at Z mod 3Z. So what are the elements in this factor ring? Well, they are cosets. So let's remember how cosets work. So 3Z, that is all the multiples of 3. Minus 9, minus 6, minus 3, 0, 3, 6, 9, and so on. And then we have 1 plus 3Z. And that's all the multiples of 3 plus 1. So that's minus 8, minus 5, minus 2, 1, 4, 7, 10, and so on. And then we have all the multiples of 3 plus 2. So that's minus 7, minus 4, minus 1, 2, 5, 8, 11, and so on. And so that's it, right? We partitioned Z into these three cosets, 3Z, 1 plus 3Z, 2 plus 3Z. So those are the elements in our factor ring. Now the question is, how do they behave under addition and multiplication? And that's what our two tables are for. So let's fill in the addition table and the multiplication table. So 3Z times 3Z, that is just 3Z. So I get 3Z right here. And then 3Z times 1 plus 3Z, according to our multiplication rule up here, this is really 0 plus 3Z. Let me clean this up a little bit. This is really 0 plus 3Z. And according to our multiplication rule, that is 0 times 1 plus 3Z. Oh, I'm doing multiplication. Oops. Okay. Well, since I'm multiplying, let's multiply. So that's 3Z over here. And apparently, when I multiply 3Z by anything, I get 3Z back. So this is 3Z. This is 3Z. And also in our first column, this is 3Z, and this is 3Z. So that's already a lot of our multiplication filled in. What about if I take 1 plus 3Z and multiply by 1 plus 3Z? Well, that is 1 times 1 plus 3Z. So that is 1 plus 3Z. Okay, so I get 1 plus 3Z over here. And then similarly, I get 2 plus 3Z over here. And I'll get 2 plus 3Z. And then 2 plus 3Z times 2 plus 3Z, that's 4 plus 3Z, but 4 mod 3 is 1, so that is really 1 plus 3Z. Because 4 plus 3Z is in the same coset as 1 plus 3Z. So that's our multiplication table. Let's do addition. Well, addition, we have 3Z plus 3Z. Well, that's still 3Z. And then I have 3Z plus 1 plus 3Z. That is 1 plus 3Z. And here I get 2 plus 3Z. Here I get 1 plus 3z, 2 plus 3z. So addition we are pretty used to. This is 1 plus 1 is 2 plus 3z. Then I have 1 plus 2, that's 3. But 3 plus 3z is the same as 3z, so I just have 3z. 2 plus 1 also 3z over here. And then finally 2 plus 2 plus 3z is 4 plus 3z, but 4 plus 3z is the same coset as 1 plus 3z, so I have 1 plus 3z right here. So those are the addition and the multiplication tables for our factoring. And let me clean up a little bit, because let's examine these addition and multiplication tables. So which of our elements behaves like should be the additive identity? And do we have unity? Well, 3z right here, that behaves like our 0 element. Or 0 in the mod 3z. So if I multiply anything by 3z, I get 0 back. So everything multiplied by 3z gives me 3z. That's how the additive identity behaves in a ring. And then here 1 plus 3z, that is unity. So we can also see that in our in our multiplication table. Part B, you can stop the video and do part B, and I'll be back in the next video to talk about just the solution of part B and then a few results that we have